Okay, so our topic is how derivatives reveal the shape of a graph. Okay. So again, the tools that we are going to use is, well, not many tools, just mean value theorem. Okay. So mean value theorem confirms our expectation that if the derivative is calculated, derivative tells us how fast the function is changing. That was our intuition, expectation. Okay. So mean value theorem tells us that is the case. Okay. So first, we check that the derivative tells us if f is increasing or decreasing. Okay, so we have f differentiable on AB, so the derivative exists. Okay. By definition, note that we say f is increasing if f of x. Okay, so let's use this suggestive notation that we will later use. Minus f of x1 is positive for all x1 less than x2 in A, B. Okay, so on A, B, you take two numbers, x1 here, x2 here. If the value of the function here is larger than the value of the function here, we will say that it is increasing. Of course, here you have to check it for all pairs. Okay, so mean value theorem comes handy here. Okay, so by mean value theorem, we have f of x2 minus f of x1 is, I divide this by x2 minus x1, so I multiply it over here, x2 minus x1 times f prime c. So c is some mysterious points in between. Okay, for some c. In this case, I know that x1 is less than x2. So instead of saying between x1 and x2, I write precisely the interval. Okay. Okay, now you see that this is always positive. Because that's how I chose. x2 is larger than x1. So the sign of the left-hand side is dictated by the sign of the derivative at c prime, at c. Since I don't know where c is, okay, mean value theorem is an existence theorem. It says that there is a point where the derivative, if the derivative evaluated there, you will have this equality, but it doesn't tell you how to find that point. Okay. So I have to, in order to make use of this equation, I must put a condition saying that everywhere the derivative is of the same sign. So for example, if the derivative is always positive, okay, so this part is positive, then this part is always positive, okay, then this holds. Okay. Now here, since this is always positive, the sign of the left-hand side, okay, so that's correct, right? Left-hand side is dictated by this sign. Okay, so now by looking at this, we can immediately say the same thing. Okay, so if f prime is positive on A, B, then f is increasing on AB. And if f prime is negative on AB, then f is decreasing. Okay, so that is the, so this is the information that the derivative tells us. Okay. Again, the usual format of a theorem in mathematics. We put an extra condition, and we check that under that extra condition we have something useful. If the derivative is always of the same sign throughout an interval, then the function is either increasing or decreasing through that. Okay, with the words increasing and decreasing, there is some confusion in the literature, because some books say that when I say increasing, I definitely mean this one. Okay, some books says that I will say increasing when I allow equality here. Okay, so then there is this word monotonic, etc. Okay, but we are not entering into that. Every time equality is required, we will explicitly mention it. Okay, so there is, because if you want to use pedantically correct terminology, then you will say that this is non-decreasing. If you put equality here, it is non-decreasing. If this is the case, it is increasing. Okay, then everything, at least for me, everything becomes confusing. So some non-decreasing thing is actually increasing, but sometimes it is equal. Okay, so let's not enter into that terminology. Okay, so let's do, okay, so here I said, let's look at example 1. So what does example 1 says? Okay, so the way to use this is, of course, to check where these conditions hold. Okay, so where is the derivative positive, where is the derivative negative? That's how you use these things. Okay, so how to make use of this thing? This result. Okay, so given differentiable f, find the intervals on which f prime has the same sign. Okay, so you see this again involves solving equations, because you calculate f prime, equate that to 0, find the roots. So in between the roots, it must have the same sign. Okay, because if it changes sign, there must be, by intermediate value problem, it must have a root if f prime is continuous. Okay, so that's, I think that's the example in 1. Find where the function is increasing. Okay, so this is a horrible function, but since it's an example, apparently we will be able to factor it. So, okay, let me write it here. Okay, so example. F of x is equal to 4th power of something, 3x to the 4 minus 4x cubed minus 12x squared plus 5. Okay, so so we want to find, the question here is to find the intervals on which the function is increasing and decreasing. Okay, so we calculate f prime of x. This is 12x cubed minus 12x squared minus 24x. Okay, right? Let us, now in order to solve this, the easiest way is to factor it. Okay, so since it's a cubic, well, fortunately it is divisible by x. It is also divisible by 12. So this is 12x times x here minus x squared minus x, okay, and minus 2. Okay, how do I factor the right-hand side? So apparently one root is 1, one root is 2, plus or minus. Okay, so what is it? 12x 12x x minus 1, x plus 2, no, x plus 1, x minus 2. X plus 1, x minus 2. Okay, correct? Okay, now we want to find the intervals on which f prime is positive or f prime is negative. Okay, so we know that at x equals 0, it is 0. At x equals minus 1, it is 0. And x equals 2, it is 0. So in between, this is a continuous function. The derivative is a polynomial. It's a continuous function. So in between, it will have the same value. Okay, so suppose on this side, if x is very negative, what happens? Okay, so this is negative. If x is very negative, this is negative. This is negative. So 3 negatives will be negative. Okay, so sign of f prime here, it will be negative here. So let us say it is 0 here, 0 here, 0 here. So what happens here between, this is negative, this is positive, this is negative, so plus, right? Well, I'm tempted to write this thing because experience tells you that if there is no repeating root, then the sign alternates, right? The sign will not alternate. It will be plus here and also plus here if this is a double root. Okay, so in this case, since the roots are simple, okay, so f is decreasing here. Okay, so this is the sign we use for decreasing. It is increasing here, decreasing here, and increasing here. Okay, so this gives you a shape, idea about the shape of the graph. So let's check if it is given in the book. Okay, so it is given in the book something like this. Of course, now we don't know how far it goes down here, but we don't know how far it goes without calculating. The first derivative gives us only this much information. Okay, so that is one thing. Okay, and by looking at this picture, we see something. The curve is going down and going up. At this point, the curve has a local minimum, right? The derivative is 0. So this is a candidate for a minima or maxima. Okay, so here it is a local minimum. And at this point here, again, at this point, it's a local maximum. Here it's a local minimum. Okay, so we have candidates for local minima and maxima. Here it is increasing. This is a polynomial, so we don't expect this to go asymptotically somewhere. This goes to infinity here. This goes to infinity here. Okay, so these I'm reading from the equation of the function. The function is a polynomial, so it doesn't asymptotically approach a horizontal asymptote. It goes to plus or minus infinite, depending on the first term here. Okay, so this function has no maximum. It has a minimum, global minimum, which I know from this picture. Okay, it comes from infinite and eventually it goes to infinite. So here it has a local minimum, okay, and here it has a local minimum. One of these is absolute minimum. Okay, so what I learned from this picture, I formulate. I say that a point is a local minimum if the derivative changes sign from minus to plus. Okay, so it is obvious on this picture, but sometimes the function is complicated. So all you have is to look at the derivative. Okay, so the sign of the derivative gives us hint about whether it is minima or maxima. So let us formulate that. Okay, so we learned from this, we observed from this example the following. Okay. If f prime c equals 0 and f prime changes sign from negative to positive at c, okay? So before c, it was negative. Negative means the function was decreasing. Here it's increasing. Okay, so we are just reading this information, making it into a rule which will apply for all functions. Then c is a local minimum for f. Okay, so we insist, of course, that it is local. There may be several local minimums. One of them will be global minimum if the function is not going down to minus infinity. Okay, so we have to use common sense to check if one of them is global minimum. So similarly, if f prime c is 0 and f prime changes from plus to minus at c, so it is one of these things. To immediately to the right of this point, in some neighborhood, it is plus. So we are not exaggerating. We are not going here and saying, but here it was negative. The understanding here is that just around that point. Okay, so again, common sense. Then c is a local maximum for f. Okay, so similarly, we don't claim that this is going to be a global maximum because, for example, in this picture, the function goes up to this and then goes down here. But when it goes up, now I go to the function, I realize that it goes to infinity. So this function is just a local maximum, not a global maximum. Okay, so these are okay, but if f prime does not change sign at c, we don't know anything. We don't have any information about f of c. Okay, so this again comes from experience. Normally, if you didn't have any experience at this point, you would ask what happens to f, what is the significance of f of c if f prime does not change sign. It is negative to the left of this, and it is also negative to the right of this. You would check. And in science and in engineering, you should always first try the simple cases. Okay? If the simple cases don't tell you anything, then you try more complicated things. But the simplest cases are functions f of x to some power. Okay? So let us look at f of x, for example, x cubed. What happens to this? Okay? So f prime x is equal to 3x squared. F of f prime 0 equals 0. And f prime is positive on both sides of 0. Okay? The graph is something like this. Okay? So we all know the graph of this. It is like this. Okay? So at this point, you see the derivative is 0. But to the left of this, the derivative is positive. The function is increasing. Here, the function is increasing. So nothing happens here. Okay? Also, we can have f of x equals x to the 4. Okay, so f, no, here it changes sign. No, x to the 4 changes. Okay, so that may not give any example. Okay, so one example is enough. It tells us that this is not, the question we had in mind is whether it is a local min or local max. Okay, so this one example tells us that if the sign doesn't change, it may not be a local min or local max. Okay. So the next thing is what does the second derivative say about the graph? Okay, so the second derivative is the derivative of the first derivative. Okay, so derivative tells how fast this function is increasing. So the second derivative gives us sort of acceleration, how fast the speed of the graph changing. Okay, if the speed of the graph is increasing, okay, so the graph is increasing, but then it wants to increase faster and faster. Okay, so you expect this thing to curl up a little bit. Okay, so let us see if this expectation, this common sense expectation, is also confirmed by algebraic equations, so that we answer the question, can we trust algebra in these cases? Okay, so how about the second derivative? Okay, so it means what information do we get from this? So f double prime tells us how fast f prime is changing. Okay, so f double prime positive tells us f prime is increasing. Okay, so f prime is the slope of the tangent at that point. Slope of the tangent at that point. So if at one point the slope is, say, this one, then at the next point the slope is slightly different. Okay, you move a little bit here, the slope here is now larger. Okay, so the slope increase. You come here, the slope increase. So you look at this shape, you expect the shape of the function like this if the speed is increasing. Okay, and similarly, if f prime is negative, then so if this is, then f prime is decreasing. So again, the same interpretation. At this point, the slope was like this, but then the slope decreases. The slope becomes like this. Then the slope becomes like this. So you expect the shape to be like this. Okay, so this is what you expect by just using your imagination. Okay. It turns out that these are the case, so we give a name to this. Instead of every time describing that the shape is something like this, we give a name to this. Okay, so name, such a thing is called concave up, and such a thing is called concave down. Of course, in a minute we will write formal definitions for concave up and concave down, but first we said, let us give a name. Now we could have called this convex down, and we could have called this convex up. Okay, so the only reason why we choose concave over convex is just a human preference. If something is down and it corresponds to something positive, for some reason it confuses us. Okay, positive and up. Okay, we match them in our mind, so we say, okay, let us call this, let us use concavity so that up corresponds to positive and down corresponds to negative. Okay, so if we hated students, we would do it the other way around. This would be convex down, the other one would be convex up. So that tells us how much we love you. Okay, so let's give an explicit definition of concave up. Okay, so definition. A graph. Okay, so let us give a name to the graph so that in the definition we can use it. The graph of y equals f of x is concave up. You see that in order to use this, concave up can be only on some interval, because we can have graphs like this. You see that this part is concave down, this part is concave up, so we have to talk about regions, okay? So concave up on some interval a, b, if. Okay, so I don't put a, now I turn you and make a definition so that everybody understands it, and while making the definition, you don't define something which you don't have in your mind, because sometimes that happens. You give a, oh, sorry, sometimes you give a definition, it explains the most common example, but then people come up with examples which you don't agree, but still that fits to your definition. So you have to give a careful definition. What will be the definition of, yes? Okay, that's good, but that's calculation. Now we are trying to give the definition with, you see, we are saying here the graph. Your definition is correct, but now we want to give the definition of only for this function. We are not assuming that f is differentiable or not. I just draw it by hand. Still, you see, this thing makes sense. Forget about the tangent lines. You just have this graph. This can be a non-differentiable continuous function. Those things do exist. Okay, so the definition should not rely on the definition should not rely on the derivative. Can we have such a definition? Just because I want it doesn't mean that it exists. Can we invent a definition? Yes?
There is x1, x2, and x3. x1 smaller than x2, smaller than x3, and f of x minus f of x2 minus f of x1 smaller than f of x3 minus f of x2. I mean, the difference is increasing.
No, I don't know. That's too complicated. Maybe it is wrong. So I'll bet my money that it is wrong. It is wrong. I don't claim that it is wrong. I'll just put my money and we'll check that I'll get your money. It's too complicated. If you give such a complicated definition to define something, I'm sure that if we think for 5 minutes, we'll come up with a function which obeys your definition, but you look at the function and you say, no, this is not what I wanted to define. So you have to give the definition in a very simple way so that we cannot sneak in strange things which are not concave up, but the definition is acceptable by everyone. Okay, so your idea was correct. You start with 2 points, compare something, but think about this. So what is your idea?
We can say there's an x and x minus c and x plus c. The difference between x and f and x minus c. Yes.
So I'm not. So let us agree that we don't want to give so much in the definitions. We don't want to give so much x1, x2, etc. Just words. Can you describe things just by words? What do you expect from a concave up graph? What is?
The tangent line is above the curve.
Huh?
If the tangent line.
Let's not talk about the tangent line, because we are not assuming that the function is differentiable. If the function is not differentiable, it will not have a tangent line. But everything has a second line. Well, here I objected to your friend because he is using first derivative. Now we are using second derivative. Okay, let's see have your idea.
If we take a point C in the interval AB and then find the slope of secant line.
No slopes. Our theorem will define. We want to agree on a definition of this concavity. And then in the theorem, we'll say that if the function is differentiable, it is easy to decide whether it is concave up or down, because you see we have the fact here. If the second derivative is positive, it will be concave up. But then, okay, so we want to define concave up for a continuous function only. Okay, so define concave up. Yes? Eh? Well, this function is also increasing, but it is concave down.
No, rate of increase.
Rate of increasing is the derivative. So the function does not know derivative.
If the graph seems like right side of a circle, it's concave up.
Yes, you are close now. What does the right side of a circle look like? That's what you want to describe. Okay, let's. Okay, so everything has a second line.
Other than the points on the graph, every point on the second line is bigger than
Yes, that's something which a continuous. That's something which a continuous function will recognize. Okay, because every graph has a second line, whether it is differentiable or not. Okay, so we have. This is our graph. Now we are trying to describe this. Choose any point. So this is A, this is B. Okay. So I'm modifying your definition a little bit, because your definition, if you only check A and B, then we can have something like this. Okay, so you see everything is below the second line, but this is not what you have in your mind. So now we are trying to formulate what you had in your mind with the relation between the curve and the second line. Choose any 2 points here, okay, and look at the second lines here. And no matter which 2 points you choose, the curve will be below the second line. Okay, so now that excludes this case. We don't want this. Everybody agrees that we don't want this. If you use the seconds in this way, then such things will be excluded, which we don't want also. But here it makes it clear that what we had in mind is explicitly expressed here. Okay, take any 2 points on the curve. Okay, so this is a continuous function. Take any 2 points on the curve, join those 2 points by a straight line, and check if the graph of the function is below that, above that, or intersects this. So we are saying that of these 3 cases, we'll only choose the one where the graph always lies below the second line. Okay, now agree, we didn't use derivative. We used only the graph of the function. Okay, and we don't want things breaking up here, so we use continuity. Okay, so that's the definition of concavity. Okay, so we will say the graph of y equals f of x is concave up on the interval AB, or, well, what the heck, let's say AB, if for all x1, x2 in AB, the graph lies below the second line joining. Okay, so what is this? x1 f of x1 and x2 f of x2. Okay, so now that makes sense. We are also, let's say, f is continuous for this thing to be. Okay, so take f continuous. Bunu gelecek hafta hatırlat. Because this week we are not having a quiz. Onun için söyledin değil mi? Kim söyledi? Kim hatırlattı? We are not having a quiz this week. So you came for nothing, yeah? Okay, just kidding. Okay, so next week we'll have our quiz, and now I expect you to make this reminder next week. Okay, so let's say similarly for concave up, let's not spend time on it. So similarly for concave down. Okay. Now this experience tells us that now we can write a theorem that your friend was suggesting in a minute ago. We can decide whether this is concave up or down without using the definition. Okay. You see, the definition tells us to check infinitely many pairs like this. Check all possible pairs. If the graph is always below this, then it is concave up. Okay. Now the theorem says that if you use the second derivative, this is guaranteed. Okay. So theorem, if f prime second derivative is positive on a b, then f is, or rather the graph of f is concave up, concave up on a b, and if it is negative on a b, then it is concave down. Okay. Now you can use mean value theorem to you have to prove these things, but now you see we are convinced here that it will work, and we also know why it is working because the first derivative is increasing like this. So you can use the mean value theorem maybe twice to show that these things hold. Okay, so I will not go into the proof. Next thing is to define inflection point. Again, we define inflection point geometrically. Okay, so here we define concavity and concavity up and down geometrically. Inflection point is where the concavity changes. Okay, so let's make another definition. Why we make these definitions? Because you say you can't sit in a room and say, let me develop some theory so that I'll make students miserable. You play with these things, okay? Lots of examples come out, and you see that certain examples are coming up very often. So you say, okay, I'll give a name to these examples, and then you show that under certain cases, those examples always show up. So you don't do those calculations again, okay? So you just check the conditions. If these conditions hold, then I know what will happen. Okay, so that's how science develops. You play, okay? In the beginning, you start playing. So you draw graphs of these polynomials, etc. Polynomials are easier. You see that at certain points, concavity changes. Okay, so those are, of course, interesting points when you are drawing the graph. And now, next question is, how do you find those things? So first, we define concavity. Our interesting points are where concavity changes. We'll call them inflection points. Okay, a point is called an inflection point if at that point, inflection point for a function, of course, you don't just put your finger on a point and call it an inflection point. There must be a function related to it. So an inflection point for a function, if the concavity of the graph of the function changes at that point. Okay, so we are defining these things for continuous function, and given a continuous function, there is no way that I know you can pinpoint these inflection points or minima points, maxima points. You can only approximate. If you have some idea about the function, you can only try to approach those points by trial and error. But we impose a condition. We say the function is differentiable. In fact, it has a second derivative. Then we can find these points. Okay. So theorem. Okay, in the theorem, now we are saying under this condition, inflection, you can find inflection points if you check only this algebraic condition. Okay, so concavity depends on the sign of the second derivative. If the second derivative is changing sign, say going from positive to negative, if this is continuous, if the second derivative is continuous, if it is changing sign, then it must cross the 0 line. Okay? You have a continuous function, positive here, negative here, so somewhere in between it is 0. Okay? So at that point, the concavity changed. Okay, so here we are saying that, let us assume that f is okay, C2. This is short for saying that the second derivative exists and is continuous, or you can just write it inverse. Okay? Then an inflection point is where f prime is 0. Okay, so this is not claiming that if the second derivative is 0, that's an inflection point. It is saying that you look at the points where the second derivative is 0, then some of these are inflection points. Okay, because a function, for example, consider the polynomial y equals x squared. It may be the second derivative of some function. Well, actually, it is the second derivative of x to the 4 up to a constant. Okay, it is 0 at 0, but it is always positive on both sides. So the second derivative is 0, but it's not an inflection point. Okay, but look at the function x cubed. Now, its second derivative is x. Okay, it is 0 at 0, and we know that 0 is an inflection point. Okay, so this theorem is saying that if you are looking for inflection points, solve this equation algebraically. Okay, solve this equation, then these are the candidates for inflection points. It's just like Fermat's theorem. You find the points where the first derivative is 0. These are candidates for minima and maxima. We know from experience that minima and maxima may not exist. If it exists, it may be at some other point, but these are candidates. Okay, so that's our understanding of concavity. Okay, let me write down formally the second derivative test for minima and maxima so that next week we formally continue from here. If I leave this to next week, I will have to remind you all of this boring stuff again. So let us do this once and for all, and then we do interesting things. Okay, using all these things, we have the second derivative. So back to our original question. So we are doing all these things to find minima and maxima. Finding mean and max. Okay, so f is continuously differentiable. Okay, so C2. Okay, so f is twice differentiable on, say, AB. Okay, so we have f prime c equals 0. Okay, so is this a local mean max? Okay. If the function is simple, there are several ways of knowing this. You look at the sign of the first derivative, you roughly plot this and see this. So here we are giving a purely algebraic way. Okay, so what can happen here? This can be, so I'm exaggerating, of course. So this can be c, the derivative is 0 here. This can be c, the derivative is 0 here. And this can be another example. Okay, so this is neither local mean nor max. This is an inflection point. Okay, so this is local mean. This is local max. Our observation here is that for local mean, this is concave up. This is local mean, and the graph is concave up. Nereden buluyorsunuz bu sesleri ya? Local max corresponds to concave down. Okay, so this is what I see from the figure. Now I want to change this to algebra. Concave down is what? F double prime negative. Okay, here f double prime positive. Okay, so now I write this part. This part is the second derivative test. Okay, I don't look at the graph. So this tells me that if I see this at the point, okay, so if f prime c is negative, then c is a local maximum. Okay, so by looking at this, I understand this. If f double prime c is positive, then c is a local minimum. Here I have to add that, and f double prime is continuous. Okay, so instead of writing this whole thing, okay, so this whole thing is summarized. So this f is C2 on AB. Okay, so that's why we invent names. Okay, the second derivative exists at every point, and the second derivative is continuous, so C2. Okay, so this is the second derivative test. So let me write this, and we'll stop. This is the second derivative test for minima and maxima. You apply this at critical points. Okay? Because you see at this point, the second derivative is again negative, but all by itself, the negativity of the second derivative does not tell you that it is minima or maxima. You only check it at critical points like this, when the first derivative is 0. Okay, so this is the theory that we summarize from high school. And so tomorrow you have your exam. Next week, I will be together with the survivors, and I'll continue. Good luck.